everyone. I really just wanted to give a brief talk on how to teach epidemiology in Web v Python. Now, this was a topic that we covered in computational biology, which is a class I teach. And to make it interesting, we used the zombie apocalypse as an example. It was close to Halloween. So let me just run through the basic model first. So we started off with an ODE model, and here's the basis for this ordinary differential equations. So there are four populations. There is the susceptible population, the infected population, the zombie population, and then the removed population. Now, as you go from susceptible to infected, there's a rate which depends on the concentration of susceptible and the concentration of zombies. Because basically the zombies are interacting with the susceptible people and then biting them to convert them into zombies. But they don't convert straight away. Instead, they turn into what's called the infected population. Now, the infected population can remain at that state for a period of time, like a latent period. And rho is the rate at which those infected then turn into zombies. So we have this middle term, which is converting infected into zombies. Now, the zombies are effectively not dying, natural causes or in any other way. The only way in which the zombies can be killed is if a susceptible person kills the zombie. And so there's a term which is alpha SZ, which is basically saying that as the susceptible people and the zombies interact, there's a chance that the susceptible person will kill the zombie. And then they become part of the removed population. Okay. Now, based upon your favorite zombie movies or zombie TV shows or zombie video games, those equations could vary. And that's one of the things that I really love about these models is that I can try to explain how the terms arise and how terms could change based upon examples of zombies or zombie movies that my students may or may not, like. So here's the basic equations anyway. So the derivative of the susceptible with respect to time. The susceptible people are being reduced primarily because of the interaction between susceptible people and zombies. And that's this negative term. There is also the capital Pi, which is the birth rate, and the delta S, which is the death rate. Those two, though, would be expected to be pretty small, considering it's the zombie apocalypse. We also have the rate of change of the infected population. So that beta SZ term that was negative in the susceptible is positive in the infected, because as the zombies are biting susceptible people, they're removing those from the susceptible population and they're appearing now in this infected population. Rho is the rate at which the infected become zombies, and so that's a negative term in the infected population, but then is a positive term in the zombie equation for the zombie population. So as the zombies are being created from the infected, they are also being reduced by this alpha term. The alpha term represents a susceptible and a zombie interacting, and then the susceptible person killing the zombie. So we see the zombies being removed from the system based upon this term. And then that term pops up in the removed concentration. So we're removing them then from the system. We assume that once the zombie is being killed by a susceptible person, it is a undead. So here's the basic model then. So the code is relatively small, including the code to plot this. And I've included a small term that slows it down so that you can actually see the populations grow. The infected suddenly increase and then the zombies taking over. And this is quite a bleak scenario where the zombies inherit the earth. But that's the kind of the model that you can implement in GlowScript or Web v Python as it's now called. basically you can have the populations evolving in this plot as the simulation is running. And that's one of the things I really like about it. It gives a really nice visual that the students can implement very easily in their code. Moving on, where the most complicated thing we do in this week's lecture is we implement the model in both stochastic, which means we're randomly selecting events to occur now rather than just updating the ODEs, and spatial, so we're now allowing it to move around on a lattice. Now, stochastic is especially important for very small populations, and that's the reason why we're using it here, because one zombie could literally start the whole apocalypse, or a susceptible person could kill it and then could end the apocalypse. So the first rate is the rate of zombies infecting the susceptible. Here we don't have an infected population, so we're assuming kind of similar to some like World War Z or whatever, where you don't necessarily stay infected for very long, right? Upon being bitten, it's quite quickly that you become a zombie. We also have the susceptible people attacking the zombies, and then the zombies would decrease by one, and the removed would increase by one. And in both of these equations, the little subscript I just represents a location on the lattice. So these rates would happen everywhere at every single lattice site. We also have the probability of moving around. So this is given by mu s times si. That's the rate at which it's moving around. And now I and j are two neighboring sites. So we assume that the susceptible people can move to a local site, and it would be decreased at the site it's at and increased at that neighboring site, the number of susceptible people. Now, in some models, you might include like air travel and longer range sort of movements, but we're going to assume that during the zombie apocalypse, there's not much air travel. And the same thing with the zombies. The zombies are going to be able to move around with this mobility, this rate of moving around, which is given by mu. Now, to find the probability, we're going to need to take the rate at which something happens. In this particular case, we're looking at the transmission rate, divided by all the rates in the system. And so this gives us a probability that goes from 0 to 1, right, as you add up all the probabilities in the system. In other words, we're going to assume at the next time step something is going to happen, right? So one of these things is going to happen. And then this is how we calculate the time. It's just 1 divided by all the different possible rates in the system. Now, to make sure that we select a probability that obeys these correct probabilities, what we're going to do is we're going to define the cumulative distribution function. The cumulative distribution is basically just adding up all the probabilities, and then what we're going to do is we're going to say, as we're adding them all up, as we add a probability, if by adding it we jump over a random number between 0 and 1, then that is the event that we're going to select, right? And because each time you're adding up the probabilities, if you add a bigger probability, then you've got a greater chance of jumping over that random number. We're going to basically select a random event that obeys the correct probabilities, right? So we got the correct statistics in the system. And then here's a little video of the simulation running. This is running in real time. So in this one, the zombies aren't moving around too much. They're sort of staying locally. Now the grey is the susceptible population. So it looks kind of noisy because I start off with a roughly around 5 susceptible people, but I add a little random number to it. Now, the susceptible people aren't moving around because to have them move around takes a lot of time. And so, for a student simulation with this many susceptible, decided to ignore it. That might not be the case if you had less susceptible people to begin with, though. And the zombies are this red dots. So as their sort of numbers of zombies increasing, it gets darker. And you can actually see behind the red, there's regions of white, which is basically where the zombies have killed all the susceptible people. Now, what we're going to do with this model is we're going to run it again, but this time I'm going to make the zombies much more mobile. So now they're running around like crazy. I've actually sped up this movie a little bit just because the time step is reduced because of the zombies just moving around a lot more in the system. And then sort of spreading out a little bit. So this might be more kind of like the 28 days later as opposed to the Night of the Living Dead kind of zombies that maybe we simulated in the last little video. But that's sort of how the simulation works. And it's sort of interesting to think that, in order to plot this, what I do is I created an array of I created an array of cubes and then just colored those cubes based upon the populations. So it was really easy to do in GlowScript, and that's kind of one of the great things about GlowScript is its ability to incorporate the plotting, but also to incorporate graphics. So here's a picture of a forest fire model that I actually do with the students, I think in the second week. And being able to incorporate, cones in this case, because this represents the trees, or you can do spheres or cubes, any way you want in a three-dimensional system. And so that's really what makes this WebVPython so powerful. The other thing I really like about it is that it can be run in a browser, so students can run this on their own laptops, on their own computers. They don't need to download things or have to install anything. All they do is they open up a browser and they go to the website, and everything runs within that website. And then when you're done, if you want to, you can actually copy embed code and then paste it into HTML. So you can actually have these things running within other websites. So just to clarify, or just to conclude, I found it's a really wonderful way to explore not just epidemiology, but lots of computational biology in the classroom. And I'm sure it'll be useful for lots of other topics too. Thanks for listening.